In this video, we're going to be covering section 7.1 in your textbook. And we'll just go ahead and dive right in here. The uniform probability distribution is one where the probability density is the same everywhere across an interval from A to B. So you can remember this because the word uniform really does mean the same, right? Just like in school, if you were part of the marching band, you wore a uniform. The idea of wearing a uniform is that everyone looks the same. And also remember that the sum of all probability must be 1 for the uniform distribution. And so just to give you a quick example, hold on. So here is Microsoft Excel. And when we type in equals RAND here in Microsoft Excel, what we're going to do, what it does for us, what Excel does for us, is it creates a random number between 0 and 1 where the probability density between 0 and 1 everywhere is the same. So every time I hit it's going to calculate a new random number between 0 and 1. But again, what I want to point out about the probability density being uniform, that means that it's just as likely to get a number close to 0 as it is to get a number that's close to 1, as it is to get a number that's close to half. Everywhere the probability is equal for generating these random numbers. And I also put a nice visual together for us to look at. So if we follow this link to desmos.com. This thing here in blue, this little rectangle, represents a uniform distribution. So the lower bound I'm calling A, the upper bound I'm calling B, and A and B are just points along my space of possibilities. And so for the example that I had with Microsoft Excel, I said that I was going to generate a random number between 0 and 1, meaning my lower bound is 0, my upper bound is 1. The height of this rectangle represents something we call the probability density. And so notice that anywhere between my lower bound and my upper bound, I have the same probability density. In this case that I just created, the probability density would be 0.68 or so. And the key here, and the reason why whenever I stretch the bounds farther apart, this probability density decreases, and whenever I push these bounds closer together, the probability density increases, is because all probabilities must sum to 0. Now the sum of all probabilities, in our case, is going to be the area shaded light blue here. So the area underneath this probability density curve, that is the total probability. And so you can see whenever I make my space of possibilities just between 0 and 1, my probability density becomes 1. And of course that's because 1 times 1 gives me an area of 1 here. And of course if I make my space of possibilities just from 0 to 1/2, then my probability density becomes 2. So that 1/2 times 2 still gives me an area of 1. And if my space of probabilities goes from 0 to 2, then my probability density must be 1/2 everywhere, because 1/2 times 2 is again 1. So when I'm changing these bounds, the area under this curve remains the same, and it remains equal to 1 because this is a probability density curve, and the sum of all probabilities is 1 for every random process, and because we're interpreting the area under the curve as probability. Okay, going back to what we had before. You know that every hour has 60 minutes. And let's think about at Midland Memorial Hospital, you know, they have probably like a maternity ward. You might ask the question that for any hour, you know, babies can be born any hour of the day, but for any hour you have 60 minutes. So you have like, you know, let's say this is like 5 p.m. So this vertical line represents being exactly at 5 p.m. This would be 5:15. This would be 5:30. this would be 5:45, and this would be the next hour. But what I want to point out is that I don't want to just think about 5 p.m., but I want to consider this hour-long interval for every one of the hours for the 24 hours. And just ask this very general, kind of weird question. It's kind of a weird question to ask. But you might ask, are more babies going to be born during the first 15 minutes? Being this part right here. From here to here, the first 15 minutes. Or are more babies born during the second 15 minutes, which would be like here to here? And if you think about it for a moment, there may be some sort of possibility that more babies are born during a particular month of the year than others. There may be a higher chance that babies are born during the day versus at night. But if we're considering every hour and every month to be the same, and we're only looking at was the baby born during the first 15 minutes or the second 15 minutes or the third or the fourth 15-minute period during the hour in which the baby was born, I think you have to agree that these probabilities would be the same. In fact, I think if you recorded the time, the exact time at which babies were born or pulled out, you would find that the distribution of baby birth times over the course of any 60-minute hour, as measured by the clock, is a uniform random distribution, right? You can't predict exactly when a baby is going to come out, so it makes it random. But the probability is sort of equal over the course of 60 minutes. And, I guess what I'm talking about is not a specific baby that you're currently delivering. What I'm saying is if you know you're 2 months pregnant, you can't really predict 7 months from now if the baby's going to be born at 3:15 or if it's going to be born at 3:47, right? The probability is equal, uniform everywhere. So this is one example. And I'll be honest with you, and I'll say that uniform distributions don't typically occur in nature very often. Uniform distributions are really, really useful and helpful to programmers and people who make games and people who want to run statistical simulations. It's a really important theoretical construct, and we use it a lot in computer programming. But in nature, you don't see this pop up very much. And so if this particular example seemed a little bit forced, a little bit contrived, then you're right. This is kind of a weird example, but it's actually difficult to think of situations in nature that follow a uniform random distribution. So the last bullet point here says, for a randomly selected baby, the probability density is equal for every moment during the hour in which it's born. Now, suppose you're going to deliver a baby 7 months from now. Ignoring which hour of the day the birth takes place, what is the probability that the baby is going to be born between 20.2 minutes and 40.5 minutes after the start of the hour? So 20.2 represents this right here. This is approximately 15, so that makes this 20.2. And 40.5 is going to be this point right here because this is the 45-minute mark. So this is going to be 40.5. Well, since the probability is uniform everywhere across this 1 hour period, from 0 minutes to 60 minutes, the whole uniform probability would be equal across the interval. Really, the probability that it's born between these 2 points in time, in other words, the probability that it's born in this green shaded area, is going to be this. It's going to be the width of the green shaded area divided by the total width of the interval, which in our case is 60. So 40.5 minus 20.2 is going to be 20.3 divided by 60, which is just like barely more than a third. I'm drawing a blank here. But yeah, barely more than like a third. So you can put that in a calculator. get something like 0.33-ish. I'm not going to pull out a calculator, but you will have one on an exam. Okay? Now, let's think about this situation, kind of a similar example. And what we're asking is, what's the probability that the baby will be born somewhere between the 26.4 minute mark and the 35 minute mark? Well, again, we're concerned about the relative size of this little purple shaded area to the whole interval. And so the width of that part where we're considering a success is 35 minus 26.4, and the width of the total interval is 60. And so this is going to be like 8.6 out of 60. And again, put that in your calculator, you'll get a number, you'll get a probability. What about this? So our little interval is shrinking, it seems, because now I'm concerned about between 26.4 and 27. Now the width of that interval is going to be 27 minus 26.4, which is 0.6. We divide by 60, and we get 0.01, or like just 1%. So this little slice represents 1% of the whole interval. So there's a 1% chance that your baby is going to be born between 26.4 minutes and 27 minutes during the hour, right? Now we ask the question, ignoring the hour of the day, no. Yeah, that was right. Okay, so ignoring which hour of the day the birth takes place, what is the probability that the baby is born exactly 26.4 minutes after the start of the hour? So 26.4 minutes is referring to this point right here on my number line. Well, what would be the width of that interval? It would be 0. And so actually the probability here is 0 that the baby is going to be born exactly 26.4 minutes after the start of the hour. Might seem a little bit weird, because you know that it's possible for a baby to be born at 5:26.4 p.m. It's certainly possible for that to happen, but the probability is 0. So this is one of the strange things that we run into with a continuous variable, with a continuous random variable, that follows one of these continuous probability distributions, is that the probability of the variable taking on any exact value in the distribution is actually 0. Notice that that is different from a discrete random variable, like a discrete random variable that follows the binomial distribution, for example. We can calculate an exact probability for shooting 3 out of 10 free throws. That's actually really easy to calculate using the binomial distribution probability mass function. But getting an exact value for a continuous random variable is possible, but has probability 0, because the baby could be born at 26.4 minutes after the start of the hour, or the baby could be born at 26.41 minutes after the start of the hour, or even 26.40000001 minutes after the start of the hour, or 26 plus a 1 Planck time, right, after 26.4 minutes after the start of the hour, right, the smallest unit of time imaginable, right? You can always subdivide further with a continuous random variable, and so there you have it. That's sort of why. And if that explanation isn't really satisfying and you want to explore this in a little bit more detail, let me show you where on our Canvas page you can find that. So this is our Canvas course homepage, and if you are curious to learn more, or you just need more help soaking that fact in, I want you to take a look at this bit right here under Chapter 7 that says 3 blue, 1 brown probability density. So that's a video that I would recommend. If you're having trouble rationalizing in your head why this probability is 0, then go ahead and watch that 3 blue 1 brown video. I think it really helps a lot. So for the uniform distribution, the mean is the median. Those are the same because uniform distribution is a symmetric distribution. The population mean is going to be the lower bound plus the upper bound divided by 2. That's what a plus b divided by 2 says. So it's halfway through your interval of possibilities. That's the median and the mean. The variance has a strange formula. It's going to be 1/12 of b minus a squared. And the standard deviation has the formula, well, it's just, the standard deviation is always just the square root of the variance, right? So let's compare this with the normal distribution, and just sort of compare contrast here. The uniform distribution is 0 everywhere outside of the lower bound and upper bound, right? Outside of that interval of possibilities, the probability density everywhere else is 0. For the normal distribution, the probability density is never 0. So let's take a look at our Desmos and sort of, see if we can understand that visually. So here's my uniform distribution like before. Here is a green curve showing my normal distribution. So of course the normal distribution sort of follows a bell curve. Notice that outside of my lower bound and my upper bound for this blue curve, this uniform distribution, it goes directly to 0. That probability density is 0 everywhere outside the bounds. But for this green curve, no matter how far you go out to the right, it actually never quite becomes 0, right? So just to show you where it looks like it becomes 0 here, if we zoom in close enough, we find that it's not actually 0. When we zoom in closer, we find, oh yeah, it's not exactly 0. And it's getting closer and closer and closer to 0. But it's not 0. I want to show you that even if you go really far out to the right, or like this, really far out to the left, where it really convincingly appears that it's 0 at the point -10. Right here. If we zoom in close enough, and it may have to be very, 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 very close, you will eventually find that this separates and is non-zero. So Desmos is not allowing me to zoom in close enough, actually. So that's disappointing. This is as close as it gets for Desmos. But I want you to notice that whenever I click and I see the coordinate pair, the y value of this coordinate pair is 7.78 times 10 to the power -124. Now 10 to the -124 power is a very tiny number. It's just unimaginably small, but it's not 0. And it sort of proves my point, or demonstrates my point anyways. Just a demonstration that the normal distribution gets very close to 0, but never quite reaches 0. You can always find the curve separates a little bit from the graph as long as you're willing to zoom in close enough. And this follows just because the formula for the probability density function of the normal distribution is actually it's actually an exponential function, and the exponential function is never allowed to be 0. It's always positive. Okay, so maybe I got off a little bit too much on a tangent. I just really enjoy the math of this, of understanding how these distributions work. So even though, let me just recap one more time. For the blue, for the uniform distribution, you have 0 as your probability density outside the lower bound and the upper bound, outside of this interval of possibilities, the shaded blue. But for this green curve, which represents the probability density of the normal distribution, it may look like it's going to 0, but it's not actually, right? Like here where we think it's 0, you actually just have to zoom in a little bit closer to find that there is a little bit of daylight between the x-axis and the plot. So even if the number is really small, like 0.00000694, it's not 0. The normal distribution is never 0. Just unimaginably close to 0 as you go away from the mean. Okay, again, the uniform distribution has constant probability density everywhere inside the interval, but the normal distribution never has, any sort of flat lines. It's never constant. You have more probability density closer to the mean and less as you get farther from the mean. The uniform is flat, while the normal appears bell-shaped. Uniform is used in a lot of random number generators and is very important for computer programming and computer games. But the normal distribution is actually important because it describes many, many natural processes. So lots of things that you find in nature follow a normal distribution or approximately follow a normal distribution. And if this stats course were just a little bit more advanced, we would go into why that is. Like, why is it so effective in modeling natural processes, but not in this one because we don't have quite enough math yet. Continuing and showing the ways that these are equal, as these are both symmetric distributions, which means if you consider the mean or median, well, the mean and median are the same for the normal and the uniform distribution, and the curves are symmetric on either side. So if I let this uniform go from 0 to 2, like so, then our mean or median is going to be 1, because it's smack dab in the middle of my lower bound and upper bound. And notice that these curves are symmetric around a vertical line at x equals 1 here. The total area under the curve has to be equal to 1 because the sum of all the probabilities of every possible outcome of a random variable has to be 1. Both of these are continuous random variables. We talked about how that's different from the binomial distribution because the binomial describes discrete random variables. And the probability for any continuous random variable of getting an exact outcome, like x equals exactly 1.5, the probability is going to be 0 for the probability of an exact outcome for reasons we discussed before. So here are some formulas for, being able to use the uniform and normal distribution in Microsoft Excel. So PDF stands for probability density function. That's what we were looking at in Desmos. CDF stands for cumulative density function. Quantile function is the inverse function of the cumulative density function, and we'll go over that more when we need it. And if you wanted to simulate a process that follows these distributions, these are the Excel formulas to use to generate random numbers following those distributions. In your calculator, I have those first three again. So if you're looking for the PDF, the CDF, or the quantile function for either of these distributions, this is how you could use it in your calculator. But if you need it, I'll give it to you on the instructions for using a calculator on an exam. So here are some properties about the normal distribution. So it's symmetric about the mean. The mean, median, and mode are all the same. It has inflection points at +1 standard deviation and -1 standard deviation. Each side of the peak on the left side or the right side of the mode contains an area equal to 1/2 because it is symmetric after all. And both the right and left tails approach but never quite reach 0. To recap, every probability density function must have an area under the curve equal to 1. Every probability density function must remain greater than 0 for every x value. So you can't have anything dipping below the curve because negative probabilities, that doesn't make sense. Does it make sense to say that the probability that the Broncos are going to win their next football game is -5%? Just negative probabilities don't fly. And then we also might take just a quick look back at section 3.4 for a refresher on the important areas associated with the normal distribution before we go. So here's that slide that I was talking about that shows the important areas here. So just in this sliver that this arrow is pointing to, that's 34% of the area underneath this red curve, the red curve representing the probability density for the normal distribution, hence the bell shape. So 34% of the area under the curve would be 0.34, right? Because the total area under the curve is 1. 14% would be 0.14 here in this little lilac colored region. And then this orange slice, that would be 0.021 area in that orange slice. And then again, plus or minus 1 standard deviation away from the mean in this entire green region represents 0.68. This plus or minus 2 standard deviations to the right or to the left is 0.954, and 3 standard deviations away from the mean contains 0.9973 area under the curve, or in other words, 99.73% of all the probability from the process. So if you have a normally distributed random variable, it's got a much better probability that's going to land close to the mean, even though technically it could be really far out. There's some very slim probability that it could even fall more than 5 standard deviations outside the mean. But notice that probability, 0.000029, is a very, very slim probability. So it's probably not going to land out here. It's probably going to be more likely to land close to the mean. All right, I guess in this last minute before we go, I'm just going to throw up here what it looks like for the cumulative distribution function of the uniform distribution, just to see what that looks like. The cumulative distribution function is saying at a certain point x, how much of the area under the curve have we seen reading from left to right. So going from left to right, we're accumulating more area under this blue curve. And let's see. And so like at the point like x is equal to 1.5 here, what the CDF is telling me is that we've accumulated an area of 0.834 under this blue curve. And so the rest of it is going to be over here on the right side of this vertical red line. And the cumulative distribution function, notice, ends up at 1. After you're done with the whole distribution, the area has to sum to 1. So that's why my CDF red curve here goes all the way up to 1. Likewise, let's take a look at the cumulative distribution function for the normal distribution. And that's given here in purple. So again, just like before, there's not very much area under this green curve way over here. So the purple hasn't actually accumulated very much area. The purple curve is just the running total, summing up the area underneath the green curve, right? And so when the green curve starts to have some significant area, that's when the slope of the purple curve starts to pick up a little bit because you're accumulating area faster. At around the mean, like right here, the middle of that green curve, the CDF, the purple curve, is close to half. It's close to a value of half because you've added up an area of 1/2 when you've reached the mean of the normal distribution. And then the slope of the purple curve starts to level off because the area under the green curve starts to get smaller and smaller. And so over at this point, the purple curve has a value that's pretty close to 1, but not quite, like 0.9898. It's pretty close to 1. But there's still a little bit of area over here underneath the green curve. And eventually the purple curve approaches 1 because there's not much area left underneath the green curve anymore. So cumulative distribution functions always end up at 1 when you go far enough to the right. But the idea of a CDF is it's adding up the area underneath the green curve, underneath the PDF curve. Okay, see you in the next video.